Hello, welcome to revision screencast on biomechanics. So we're going to have a look tonight at the following. So we're going to have a look at the calculations of these key terms here: force, momentum, acceleration and weight. Now you will kind of come across these in different areas of the biomechanics specification. We've looked at forces as a kind of separate kind of topic, and momentum has been talked about with regard to kind of Newton's law of acceleration, as well as acceleration here. And then we have to have a look at the kind of force again. Remember we talked about weight, which was that kind of gravitational pull from the center of mass but coming from the floor. So that's what we have to have a look at. We need to know kind of the definition of them, and then we need to know how they can be calculated from data that you might be given for a sport in action, usually linked to a sprinter, and we'll kind of have a work through how you do those. You can have a practice at them. Alongside that, we have to have a look at how biomechanics kind of links to analysis through technology. So we'll have a look at kind of three ways in the biomechanics world that kind of performance can be analysed. So we'll have a look at limb kinematics, talking about limbs and kind of how they can be analysed on computers. So you have a look at exactly what that means. Force plates, we're having a look at its kind of ground reaction force. So there's certain kind of rectangular kind of plate where people will put their force down into these plates, and then the computer will then kind of analyse the kind of proportion of the force going down, going back up, and it will come onto a graph. So we'll also have a look at wind tunnels and how they help kind of specific sporting equipment kind of reduce this kind of drag or air resistance, particularly looking at things like cycling and Formula One. Racing. So we need to know how each type of technology will be used to optimize performance, but we need to make sure when it says definition, we need uses of, we need to just be able to give an advantage and disadvantage of each. Okay, so if we have a look through then, let's start off with our calculations. So if we start off, acceleration is our first thing. So first of all, then a quick definition of it. So acceleration, the rate of change of velocity. So make sure you get this as kind of a description of that key term there. And then if we have a look at the next section there, so how do we work it out? So calculation then refers to the final velocity, take away the initial velocity, divided by time taken. Now, first up, when you hear that, you think, oh, Jesus, how am I going to work that out? Well, it's not going to be as hard as what that is. Yes, you need to know what this is, but ultimately you'll be given figures which you have to work around. And the first thing I wanted to do really is when you say acceleration, in order to make sure you don't forget what this is, I've put a little memory method here. So I've kind of reddened here or highlighted the V and the V. So and then put the time in red as well. So when it comes up in the exam, if it asks you, or give you some figures, and it asks you to work out the acceleration within a sprinter, for example, always remember that the calculation you should use, so I'll come back to that in a sec, the unit of measurement used, this is meters per second or meters per second squared. So if I just get you onto here now, the memory method then, whenever you see acceleration, just respell acceleration into avveleration or vaveleration. Because if you just remember vaveleration time instead of acceleration, that gives you these two V's here that are really important. So you're basically saying the final velocity taken away from the initial velocity, which is always zero, which makes it really easy. So whatever the end velocity is, you're just taking it away from, it's just that number because you're taking zero away from it, divided by the time taken will give you that kind of unit of measurement linked to meters per second or meters per second squared. So let's see how you go with that then. So that's kind of there. Just pause the screencast, get the stuff in, get your head around it. At the moment, it might not make massive amount of sense until you actually see the figures. So if we have a look at some figures now then, if I put it onto here, splinters split time over the first 20 meters is 2.88 seconds. So that's your first bit. Okay, the velocity at 20 meters was 6.94. So what you have to do now is try and work out, now can you remember what the thing is, what the kind of calculation is. So remember, we're looking at acceleration. So for acceleration, we have to respell it. So can you remember that? So acceleration equals avveleration. So now what we have to do, divided by time, can we work it out from here? So pause it now, okay? And now you really should be pausing it and seeing if you can work out exactly how that works. Okay, so you're working out then, which you'll always need to do. You should have something along the sides of this. So let's have a look. So you should have had kind of a 6.94, which is a kind of end velocity, take away 0, which is the initial velocity, equals 6.94 meters per second. Then you've got to divide it by 2.88. Okay, so 2.88 seconds was the time taken for this velocity to be reached. Therefore, it equals 2.41 meters per second, or meters per second squared. Okay, so that's that first bit there. Hopefully that makes sense to you. So maybe go back over that if you're struggling. Let's move on to our next definition then, force. Okay, so force, push or pull, okay, that alters the state of motion. So basically it can be any action that's a push or a pull that changes the direction of something. So ultimately what we're looking for then is a calculation for this. A key calculation for force equals the mass, kilograms, times acceleration, which you'll get the figures for. So what you have to do, just make sure there's no memory method for this, but it's always the one that I think sticks in your mind the best. So how much force you put into something will be dictated by the mass, how heavy the force is, times the acceleration, how fast it goes. So if we have a look at that, unit of measurement for this is always newtons. So just remember, anything to do with force or has mass or weight in it, it's going to be linked to newtons. So if we go on from there then, let's have a look at this. A sprinter is 94 kilograms and accelerated at 2.41 meters per second squared. So we know it's got to be that because it's acceleration there. So then what you need to do is calculate the force of the sprinter. So I'll get you to pause it there, see if you can work out what it is. This is how straightforward it is. The kind of actual remembering the definitions isn't as easy, all the calculations. But when you actually see the figures, there's not that much you can do with that really. So see if you can remember what that is. Pause it and let's have a look then. Okay, so what you'd have here, force, 94 kilograms is the weight or the mass in this case, okay, times by 2.4 meters per second squared, and that will then translate to 226.54 newtons to give you your answer there. Okay, so that's that one done. Again, if ever you want to practice these, just go back through it, or even make some figures up for yourself, and we'll certainly have a look at some in lessons when we start to practice these. Okay, so momentum. All right, so our next calculation is with regard to momentum. Momentum then. So momentum refers to the quantity of motion by a moving body. Okay, so we have to know that definition of quantity of motion by a moving body. Now, the calculation for this is mass times velocity. Okay, so we've already looked at this mass in terms of kilograms. Now we've got to look at it times velocity. So again, the specification cannot ask you to define velocity or work it out, but it has to give you the velocity in any question. Now, if it's done in this, we need to make sure we've got it as our unit of measurement now. Because it's linked to mass and velocity, we've got to have it in kilogram meters per second. Okay, so kilogram meters per second. And how do we remember this? Okay, now I look at this one, I think this is my favourite one to remember, or the easiest one to remember, because when it comes up here, we see momentum, what I'd like you to do is just to respell it. So momentum equals capital M, momentum. Okay, so we know that mass times velocity will give us our answer. We've just got to remember that mass kilograms, kilogram meters per second then, because we're doing it into velocity. So mass times velocity there, and that will help you out. So now what you need to do is, if you want to pause that, just check, make sure you've got the memory method. So momentum, mass times velocity, kilogram meters per second. So now what we have to do is see if we can apply it to some information. So a sprinter has a mass of 94 kilograms, and its average velocity is 10.44 meters per second. What you've got to do now is, can you remember the key memory method for that? So maybe pause it and see what you can do with regard to that. Okay. So memory, momentum. What does that mean? Can we have a go now? Let's see if we can answer it. Our momentum then will be mass 94 kilograms times 10.44 equals 981.36 kilogram meters per second. Okay, so that is what you're looking for. Hopefully that makes sense to you. Now, they are the three. They are the three that we've just covered that you are most likely to need. So make sure you've got those. Keep pausing, practicing, maybe changing your figures around, and I will certainly give you some chance to do that. The other one that is spec referenced is weight, but it's very difficult for them to put that into kind of figures or working out in a kind of a kind of example scenario in a paper, but let's just get it anyway. So weight, okay, gravitational pull from the Earth, okay, and if we assume that's going to be at 10 it's per second. So if we go from here, calculation for weight is mass times acceleration, but not just acceleration, because that will be a force. It's mass times acceleration due to gravity, which is pulling down from the floor. Okay, so that's that. How do we measure it? Because it's got anything to do with mass in it, it's going to be newtons. Okay, so now what we need to do from here is have a look at the following. So if we put this on now, okay, so you can just have a quick go at working it out. A sprinter has a mass of 94 kilograms, and the acceleration due to gravity can be assumed to be 10 meters per second per second. So your job now is to see if you can work that out. Obviously, it's pretty straightforward. So we'll have a look on there. Weight, 94 kilograms times 10 meters per second equals 940 newtons. Okay, so there's your calculations. Hopefully that isn't too daunting for you. What you have to just have an understanding of are the equations and the calculations. From there, you're going to get the figures in the exam. It's pretty, common sense on which bit you have to do, but it will take a little bit of practice. We'll make sure you get that right in lesson. Okay, so now what we have to do then is this kind of analysis through technology and biomechanics. First, we're going to have a look at is limb kinematics. So what this is then, it's a study of movement in relation to time and speed. Okay, so what happens if you look down here, a computer software is linked up to infrared lights that are put onto the body, and you can kind of see different movements from your limbs, limb kinematics, taking place. So for example, it can really help with adjustment of technique. So for example, you go into the lab, you wire yourself up, make sure you infrared lights on the areas that you need to go, wire up to a computer. For example, here looking at a cricket bowling action, and what the thing can do is it can kind of have a kind of screenshot of this, or kind of pause it, or still motion, and it can start to try and adjust technique. It might be kind of landing leg position in a bowling cricket. It might be to do with the arm height, the front arm kind of angle, and all this stuff can kind of change technique. So the key thing here is it can allow adjustment for techniques, but this is the definition of what it is, and then it can do it in loads of different planes of movement. So downside to it, and it's the same for most of these, it's expensive and lab based. Okay, that doesn't make it very realistic to a lot of sporting situations. So that's your first bit there. So you might just want to see now, just make sure you got it, study and movement in relation to time and speed. Then we just need to make sure we have a little bit of an evaluation of it. Force plates then. So we've done quite a fair bit on force. Okay, so what we have is, remember, Newton's third law talked about action reaction. So for every action there's an equal and opposite reaction. What force plates do is they actually look at this kind of ground reaction force. There's the rectangular plates, as you can see here. And what will happen is the force will be put down, and from that they will look at the reaction force, and this will be kind of beamed up onto a computer in a graph and show the kind of proportional electrical version of this reaction, and how hard, how high, how big the force is. So this is how you would talk about it. Ground reaction forces can be measured. Okay, when the limb makes contact with the floor, the electrical output proportional to the force applied is displayed graphically on a computer. So this will see, like for example, however much it will come back up here onto the computer, and you'll see it on the screen. And this can be really, really important for people who are trying to do things such as changing running gait and kind of distance, and getting more force so you can get your leg up higher. And it's really accurate and reliable due to the fact it's in a lab, it's being analysed by a computer. You've got specific kind of force generated on those computers coming up on the side. The downside, of course, expensive due to equipment in the lab, and of course what sometimes happens is people who are kind of analysing, it might be, for example, certain things, I don't know, let's have a look at a basketball kind of jump up, whatever. If you're doing something on here that you're analysing, it can really, people tend to change their technique because they know they're in a lab and being tested. It's really good for kind of preventing injury. It's really good for kind of preventing injury happening in the future. So these are good things about force plates. And of course, you think of this as kind of often linked to kind of biomechanics, biomechanics in the first instance, but also it's kind of linked to kind of plyometrics. You think, so people doing explosive type sports and plyometric training, this can often be used to kind of analyse the direction of the force, etc. Okay, so going on from here then, wind tunnels is your last thing. So wind tunnels has a focus on reducing air resistance. So what will happen, key thing here, it tends to improve, the focus is on improving the aerodynamics of cars and bikes. I've got an example of Formula 1 here. So what you do, you go into a wind tunnel, the wind will come back at it, and what it's looking at particularly is to look at this thing. So it's looking at ways that kind of Formula 1 cars, cyclists can actually reduce their air resistance or drag. So when we talked about whichever direction you're going, the air resistance will come back in the other way. It's looking at things that the shape of the car, the shape of trying to make a cycle helmet as aerodynamic as possible, so it reduces the amount of air resistance that happens there. And it really allows the kind of people to kind of control variables such as wind speed, wind direction, but it's expensive, and it requires very high and expert levels of kind of analysis. So again, the expense is always as the downside to these technological advances. Okay, so that's your key focus. Can you make sure you've got a good note on these? Thank you very much.